the one that approaches the larger sized ion doesn't quite get as far as this guy. It runs into that outside electron density, right? This guy's got a larger atomic radius, and so the closeness of the approach is less here than it is here. And we just said that the energy released is a function of R. That when you look at that field energy being released, it's released continually as you continue that approach. If you stop the approach at some point, you stop releasing energy. And so the take-home message is that for larger sized ions, you'll have a closer approach, or sorry, for smaller sized ions, you'll have a closer approach, and so more energy is released when this guy gets solvated than when this guy gets solvated. So your enthalpies of formation, when you dig up those tables, even if they were defined using the conventional method, you'll still see the same trends, and the trends will be that delta H is larger for smaller sized ions and for multiply charged ions. And it all has to do with that electric potential, right? The release of that electric potential energy. So that tells us about delta H. What about delta S? What do you think the change in the entropy is going to be for a solvation process? Do you think disorder increases or decreases?
Increases.
You think it increases?
The disorder? When something goes from a solid to aqueous?
See, this is kind of there's a couple different ways to think about this, and I have to search my brain and see if I've got this mapped out correctly. Yes and no. The entropy of the solution is actually going to drop, and that's because when you have your waters without that ion present, they're kind of oriented randomly. There's some hydrogen bonding, but there's a bunch of different orientations that they can have. When the ion gets solvated, it's somewhere between like 6 and 20 water molecules end up having to take on a very specific ordering around that ion. I'm not going to draw them all, but you can imagine in three-dimensional space, there's a ton of water molecules. I think there's 3 in the outside shell, and there's a bunch of other water molecules, or sorry, 3 on the inside shell, and there's a bunch of others on the outside shell. So there's a general ordering around that ion in the solution. And so the disorder decreases. So you end up getting negative values for the S of solvation due to that, the increase in the order of the ion. But you are right, when you move from a crystal and you go into solution, this obviously increases the disorder.
So that's kind of just like the difference between delta S of solution and delta S, I guess, of the
Well, see, I have to go
substance.
back and ask myself whether or not they were referring to strictly gas phase ions, or let me think about that question more, and I'll try to talk about it again on Tuesday when I'm more confident what the heck I'm going to say about it.
Okay.
But in general, you can think of that solvation process as leading to an increase in the order, so a decrease in entropy, because those water molecules have to orient themselves around each ion. There's very specific solvation structures around those ions in solution. So, but you are right, when it goes into solution, there's an increase in entropy for that purpose, for that process. So we're going to talk about the entropies relative to H plus for a second. Um, if you look at the entropies of solvation for things like magnesium, zinc, phosphate, sodium, cesium, and nitrate, and you try to establish patterns between their entropies and their charge to size ratio, the atoms that have the larger ratio of charge to size end up having more ordering. The larger their charge is, the more that they can pull those water molecules towards them in the solution and create that ordered structure around the ion. And so species like magnesium, zinc, and phosphate, which have a larger charge to size ratio than H+, will end up having a negative formation entropy on your tables of conventional entropies. The guys that have the smaller charge to size ratio aren't able to attract those water molecules and pull them in as tightly, and so they'll end up having a positive formation entropy relative to hydrogen. And so for the conventional values, it's all relative to hydrogen. So you look at the table, something with a negative sign on the S indicates that it's probably got a larger charge to size ratio. Something with a positive sign probably got a smaller charge to size ratio. So those are the basics of the energetics. We're looking at, for the entropy terms, we're looking at ordering of water molecules around the solvated ion, and for the enthalpies, we're looking at the field energy that's released when the ion becomes solvated and we have that approach of positive and negative charge, the release of that electric potential energy that ends up being manifested as heat. We said that we can do these the conventional way and define H+ as 0, or we can go try to calculate it. And the way that you calculate it is essentially this. You take the difference of two calculations. There's a certain amount of, we're looking at delta G right now. There's a certain amount of energy that's required to create a charge of any magnitude. And you can think of that energy as, say I'm trying to build a negative ion, right? And I can't pull in just a single electron from space and plot it or plant it. I've got to take differential amounts of charge and paste them together until I've developed the full charge of a negative ion. What happens then is I get my first little piece of charge here. Let's say this is a fraction of a Coulomb charge or something like that. And I put that there, and it cost me nothing to do it because there was nothing around that repelled it or attracted it. Now I want to pull in my next little differential amount of charge from an infinite space, and I'm going to paste it right on top of it. That step's going to cost me energy, right? Because this negative charge felt a repulsion from this negative charge, and I had to push them together to stack them on top of each other. I take that next little piece of negative charge and I throw that in there, and that costs me some energy. And the total work that I end up having to do to bring those small pieces of charge in from outer space and plant them together is the integral of the force times the distance, and that's Q dq over 4 pi epsilon naught r squared, or r, sorry, it's the force, ends up being Q squared over 8 pi epsilon naught r. We take dq from 0 to q. And so we just calculate the amount of energy we spend as we paste each differential amount of charge onto, onto our thing until we've got the full charge of our ion. That calculation will tell us what the Gibbs free energy change was for creating that ion essentially from scratch. So if we had a chlorine atom and we wanted to turn it into Cl minus, we would take Cl as our starter atom and we'd start bringing charge in one piece at a time until eventually we built the ion. We can do this two ways. We can think of this two ways. What we're interested right now in is knowing what the energy is to pull a preformed ion from the gas phase and throw it into an aqueous phase, right? So we've got some solution. We want to know what it costs us to take an ion from the gas phase and move it from the gas phase into here. Essentially, the way that the people that like equations and calculations, the way that they do this is they calculate what it would cost energetically to form that ion in vacuum, and then they look at what it would cost to form that ion in a solution, which is going to have a dielectric constant that's different than vacuum. And the differences between those two energies is the relative difference in the energy between the ion in the gas phase and the ion in the solution phase. And so, what you end up with, after you run those two calculations, is something, an equation, that looks like this. Now, we just showed you that calculation here. We've got the work done for charging. We're taking incremental pieces of charge and pasting them on until we've built up the total charge of the ion. We take the integral of q dq, or 4 pi epsilon r, from 0 up to the q of the ion. Q is whatever the charge of the ion is. We end up with the term in q squared over 8 pi epsilon r after we take that, or 8 pi epsilon r after we take that integral. Q is the charge on the ion. That's going to be Avogadro's number times Z, which is, if it's a doubly charged ion, Z is 2. If it's a triply charged ion, Z is 3. And then E is the Coulomb charge, so it's the charge on a single electron. So Q is Z times E, and end up multiplying that by Avogadro's number. The total work done in the charging of a species is this term here that has this dielectric constant term inside of it. What does the dielectric constant tell you? What's a dielectric? A dielectric is something that fields can be communicated through. So air is a dielectric, right? You take a charge and you put it on this side of the room, and you take another charge and you put it on the other side of the room, and you hold them next to each other, and they exert forces on each other. They feel forces, right? Lots of materials are dielectrics. Solutions are dielectrics. Water is a dielectric. You put a charge in water, and you separate it from a charge down the way, and they exert forces on each other. The dielectric constant tells you how well that media communicates those forces. And essentially what we're trying to get at here is that in vacuum, those forces are communicated more fully than they are in a solution. In a solution, the pole, the electric pole, is essentially diminished. And so if we want to do this charge building process, and in two different situations, we do it once in vacuum and once in solution, the energy that's required to pull or to push that charge on top of the other charge is going to be different depending on the dielectric constant of the media that it happens in. Air has one of the most, it's got one of the highest permittivities. Vacuum has one of the highest permittivities. There's nothing to interfere with that electric signal. And so the forces, the repulsive forces when you're building that charge are larger in vacuum than they are in other materials. In a solution, the dielectric constant is larger, and so we got a larger term here in the denominator, which means that the forces, Q over 4 pi epsilon naught, or 4 pi epsilon, is smaller. And so essentially in something other than water, or sorry, something other than air, the amount of energy required to paste these guys together is less. What we end up with when we subtract the work required to do this in some solution versus the work required to do it in vacuum is two terms that are both multiplied by the same z squared, e squared, Avogadro's number over 8 pi epsilon naught r, but the front term has this ER in it, where ER is something that's greater than 1. And so this is less than 1, meaning that the energy required to paste a negative charge together in a solution is less than the energy required to paste a negative charge together in a vacuum. I know this sounds a little bit convoluted, but basically what we just established was that it costs less energy to create a negative charge inside some media, in some dielectric media, than it costs to build that negative charge in vacuum. If it costs you more energy to build that negative charge in vacuum than it does to build it in solution, then where is the energy of that species lower, in vacuum or in solution?
Solution.
It's lower in solution, right? And so these guys that were running these equations, they basically just built it from the initial model, initial calculation, from that kind of realization that a solvent would have a larger dielectric constant than vacuum, and so the force or the energy required to build that ion would be less. So basically what that term tells us is that in a solution, an ion has a lower free energy than it has in a vacuum. That model is not perfect. We'll expand on it in just a second. But before we do, we're going to look at some of the results. If this is true, if it's true that delta G looks like this, then a plot of delta G versus Z squared over R should be linear, right? Because you've got a linear multiplier on this term, cast delta G. Guys that ran these calculations started doing this. They plotted Z squared versus R versus delta G, and they found out that it didn't quite work out perfectly. These little dots are little points of the actual delta G, and the line is what the calculation said they should have been. They found out that it didn't quite work out perfectly, and they asked themselves why, and they started thinking about their R term, and they realized that in solution, their ions would not necessarily have the radius of the individual ion, the atom. It would have an effective radius that was a product of the solvation. So a positive ion is solvated by water molecules, and once it's solvated, this unit ends up having, it ends up transferring as one complete structure, and so it has an R effective that depends on whether it's positive or negative and how the water molecules are oriented around it. And so they looked at this chart and they said, well, let's replace the atomic radiuses with an effective radius. I should have written effective down here. But when they did that, they found that their mathematical model had a much better fit to their observed delta G's, right? So basically what we're saying is that the mathematical model works if you use that R effective. This is not perfect though. There are other things that are factors. Oh, incidentally, before I move on, I just wanted to throw these up here. So we said that the conventional model says that values of delta G of solvation, H of solvation, S of solvation are 0 for water, and we said that that wasn't true. If you do kind of more advanced calculations, you find out that delta G of solvation and delta H of solvation for water are around negative 1,000 kilojoules per mole. So there's a lot of water or energy released when H is solvated by water, and the entropy is negative 130 kilojoules per mole. It turns out that as you start building these things, as you take an ion in solution and stick it in there, initially, at low concentrations, as concentration of ions builds in that solution, it becomes more energetically favorable to stick another ion in the solution than it was to stick the first one. So you stick one HCl molecule into a vat of water, the next HCl molecule that you stick in there costs you less energy. The next HCl molecule that you stick in there costs you even less energy. The next one costs less energy. The chemical potential of that ion drops as the concentrations of ions in solution build. Then you reach a point that as you start trying to put more ions in solution, the chemical potential begins to rise again. So the chemical potential does something like this. It starts off at some initial value, and it begins to drop, and then it turns back up again and it begins to rise. And it gets higher and higher. Eventually it gets high enough that you can't stick any more ions in solution, and your stuff is no longer soluble. It comes out of solution, right? Here's the reason, or here's some explanations for the reasons. We said that when we're looking at the energy that it costs to bring an ion in solution, that to form an ion in solution, that we're concerned with the magnitude of the repulsive forces as we paste together enough charge to form that ion. And the larger those repulsive forces are, the more energy we're going to have to put in to create the ion, and the smaller they are, the less energy. Something that's not vacuum, a solution, requires less energy because the dielectric constant of the media is larger, the permittivity is lower of the media. That model that we looked at just assumed that the solution had some uniform dielectric constant that didn't change with concentration. And that's not necessarily the case. What is the case is that as concentration builds, something called shielding comes into effect. And what shielding looks like is this. If I'm building an ion in a solution that already has a bunch of other ions, say I'm building a negative charged ion, I've got some fraction of a negative charge, I need to put more in on it. And this thing is surrounded by other ions in that solution. Now I'm bringing in my DQ from out in infinity, and I'm trying to push it through here. Normally, this guy would repel the DQ if it's a negative DQ, and it would cost me some energy to paste that guy onto there. But if there are positive ions outside of this, or in between the two speed or the two negative charges, it kind of interrupts the signal. And so I don't feel the same amount of force, repulsive force, when I'm trying to bring this guy into a solution that is, or into the center of a solution that already has a bunch of ions in it, as I do in the absence of those ions. And so essentially, that shielding decreases the magnitude of force that I have to use to create that ion as the concentration of the thing builds. And so, this is concentration here. And so that accounts for this downward trend in the chemical potential as the concentration of ions in the solution builds, right? We've just essentially, by adding ions to those solutions, we've lowered the dielectric constant of that material. Raised the dielectric constant? One of those. Anyway, we've minimized that energy. Eventually, you get to a point where you've got so many of these things in solution that there's an incredible amount of ordering that needs to take place. You've got a bunch of water molecules that need to try to solvate every single ion. Pretty soon your water molecules have solvated all the ions they can solvate, and it just becomes energetically unfavorable to stick another ion in solution. Basically, your solvent has a specific carrying capacity, and once you surpass that carrying capacity, it becomes energetically less easy to stick another ion in solution. And it's not, we're not talking about the forces required to push two negative charges together in this case. We're actually talking about the forces that the solution kind of pushes against that ion with and says, no, I don't want one more ion, I'm done. No more ions in solution.
Does that sort of have to do with like the solvation process, how like all the water molecules surround the ions, so like there aren't
Yeah, that's an
water
energetically
molecules-
costly process, and once you've got a solution that has, it's trying to have 1 million of those like waters solvated around a bunch of ions, it just starts to work against you energetically. Go ahead.
So when stuff like that happens, like when you saturate your solution, I know you can increase the temperature to dissolve more. So how does that actually help you dissolve more? What is that energy doing to the system?
Just knocking everything around like little billiard balls, I guess. Let me try to answer that question on office hours when I have a chance to
Okay.
think about it longer. I just want to kind of crank out with the rest of the time some exam advice. We'll talk about this later. Exam. We got entropy, we got Gibbs free energy, and we've got those solution diagrams, right? So the entropy, there's a couple of different ways that I could go about asking you these problems. Probably the standards are take a gas that's expanding, like we did with all the rest of the gases, and say, okay, well, I've got a gas that expands adiabatically or isothermally, calculate the change in entropy for that expansion. You did a bunch of those in your homework, right? You should definitely come into the exam with those problems rehearsed, because every single thermodynamics professor I've ever had has had a question like that on their entropy exam, and I'm not one to break tradition. So there'll be some kind of a question that asks you to do that. You can remember with the entropies, you can take different paths. So we have our total differentials for ds, and one of them's got Cp over T dt time plus partial of something with respect to something, dV, and partial of something with respect to something dt or dp. Go back, rehearse those problems, figure out how to do those. Basically, with an adiabatic expansion, you're going to need 2 steps. For something that's isothermal at constant temperature, you can do a calculation along an isotherm, and you can crank it out in 1 step. If something happens adiabatically, you got a cooling process, and you got the expansion, and you got to account for both of them. So you're going to need 2 steps to do that calculation. You'll probably use some kind of a constant volume cooling, and so you'll have your ds will be Cv over T dt, and then you'll have an isothermal expansion once you've gotten to the place that the temperature that you want to be at, and now you want to increase the volume. You can use an isothermal